All right, so the way this will work, I do have a rubric for how I'm going to be kind of scoring these things, but I'll put that up on Canvas. Okay. Again, I'm planning on you guys just sort of divvying up the tasks. I think that's what you've been planning on doing. But if it takes the whole time, it takes the whole time. If it doesn't, it doesn't. I'm not that concerned about that. I might have questions for you guys afterwards. The class might have questions. But other than that, Ava, Brett, and Hannah, who's joining us via Zoom, are going to present on Heron's proof of the formula for triangular area. So go ahead, guys.
Okay. So yeah, Heron's formula for triangular area. So after Archimedes, this is sort of the timeline of what happened. Rome was slowly taking over the world. So first Syracuse fell, and then Carthage was destroyed and Corinth yielded. And Carthage destroyed ensured that Romans had control on both sides of the Mediterranean Sea, which allowed them to better take over the rest of the world. And Corinth was the last significant Greek city-state before Greece pretty much entirely fell. And then after that, Julius Caesar conquered Gaul, Egypt fell to Octavian, and Britain came under Roman control. So after this, Rome had control of the entire Western world. So Archimedes was considered the last great Greek mathematician, and after Rome took over the world, a lot of what Greek philosophers found important, which was like theoretical thought, was not important to the Romans. They were more focused on engineering and advancements in that area. There was Aristotle, who was around after Archimedes. Most of his writing is lost, and we rely mostly on commentators' descriptions of his writings. He was the chief librarian of Alexandria. He did works of mathematics, philosophy, geography, and astronomy. He wrote a poem called Hermes, which was about the stars and space, and it was in poem form, which is very interesting. Yeah, as I said, most of his writings are lost. Archimedes actually dedicated at least one work to him and considered him to be a man of great talent, which is saying something because Archimedes was very focused on just math. So he came up with two things that are fairly interesting, which was the sieve method of finding prime numbers and finding the circumference of the Earth. He actually came up with a very close estimate to what we accept as the circumference of the Earth. So for his method for finding prime numbers, he started with all the numbers between 1 and 100. And then what he would do is the first number, he would see if it is prime. 2 is prime. So after that, he would go to 3. Can 3 be divided by 2? It cannot, so then 3 is also prime. And he would continue on like that. So once he found that 2 is prime, he would go on to all the numbers that up to 100 after that that can be divided by 2, and he would take them out. So then that narrows down what numbers can be prime. After that, he would move on to 3, because 3 is prime. He would then apply that to all the numbers up to 100 and divide them all by 3, and if they can be divided, then they are also not prime. And so he went like that, moving from number to number, gradually removing numbers until he was left with just the prime numbers. So he did that again with 5, and then with 7, and then that left him with all the prime numbers between 1 and 100. Then the other thing he did was he found a very close estimate of the circumference of the Earth. We're not actually entirely sure what he did because most of his writings are lost, but we have a guess. A lot of people actually doubt the authenticity of his measurement because it was really, really close to what we consider to be the actual measurement. So there's a lot of doubts as to whether or not he actually came up with it. And one thing that's very interesting about his estimate of the circumference of the Earth was that he had no doubt that the Earth was a sphere, when later a lot of people would think the Earth is flat. But the Greeks actually did know that the Earth was a sphere, and then this was information that was then lost and then rediscovered, basically. So what he did for the circumference of the Earth was there was a city in Egypt called Sin, and on the first day of summer, the sun would be directly above that city. And then on the same day, there was a pole in Alexandria that cast a shadow. So he took the angle of the shadow from the pole and found that it was 1/50th the angle of a complete circle. So he made a couple of assumptions, which was that Alexandria was due north of Sin, which is an accurate assumption, and that light hits the Earth in parallel lines, which is also a good assumption we can make. So he concluded that the alternate interior angle of the shadow was equal to call it alpha, and then he made it was an angle that represented the center of the Earth. So based on this, he was able to, using the distance between the cities, he had this equation. Sorry, that'll make a lot more sense. So it was the distance from Sin to Alexandria over their circumference, which is angle A, which was the angle formed by the pole over the total angle of the circle. The distance between Sin to Alexandria was about 5,000 stades. We don't actually know entirely how long a state is, but we're assuming or guessing based off of information that we found that it's about 516.73 feet. So the stades over the circumference of the Earth is equal to angle A over the total area of a circle, total angle around a circle, which that would be then 1/50. And then if you were to solve the equation, it would be roughly 250,000 stades, which in miles is 24,466 miles, which is really close to what we actually accept to be the circumference of the Earth, which is 24,860 miles. So he was really close. And so because of that, a lot of people aren't entirely sure, and because we don't actually have accurate description of what he did to find this, people aren't entirely sure that he actually found this, or there was someone who described it as a happy accident that he discovered it this way. So there were two other post-Archimedean mathematicians that were fairly influential. There was Apollonius. He wrote the Conics, which is a work that was sort of similar to Elements, but it focused entirely on ellipses, parabolas, and hyperbolas. It consisted of 8 books. The first 4 books were general information about the conics, and then the next 4 were more in-depth. And then the 8th book is actually lost. And then Heron, we aren't actually sure when he lived. Very little is known about him. There's an estimate put out that he lived around 75 AD, but again, we're not entirely sure. He dealt with a lot of useful questions and applications of math, rather than just the theoretical thinking. He liked to try to apply it to something. And he wrote Metrica, which was a work that was actually lost until 1986. There was a single page of it discovered in 1984, I believe. And then 2 years later, they found the entire work after believing it to be lost and completely gone. So that's my question.
So now we're going to move on to the proof a little bit now that we know who Heron is. But in the context of the proof, we need to know how to solve a triangle that we see there. So without drawing like an altitude, we really don't know how to find the area without this proof that without the formula that Heron proved. So take the triangle of sides 26, 25, and 17. And then so this is the proof that this is the formula we're gonna prove, is that the area of the triangle is equal to the square root of all of s times s minus a times s minus b times s minus c, where s is the symmetry perimeter, which is half a plus b plus c. So what we can do is we can actually solve this from the formula, and we'll plug in the values, and then it equals 204 units, basically. So this is what we want to prove ultimately. So there's going to be a lot of information. I'm not going to lie. Like Heron's proof, really what he does is he expands it. He gives a lot. And then at the end, it just kind of comes together. So we're going to go through a lot of material, and it's a lot, but just stick with it and write it out. So the first part that I want to talk about, the propositions and like just the basis of the proof. Okay. So proposition 1, the bisectors of the angles of a triangle meet at one point that is the center. So basically that's what that first picture is talking about. It's you bisect the angles of a triangle, they come to a point, and from that point you can inscribe a circle. It's not like there's no arguing that. Okay. Proposition number 2, in a right angle triangle, if a perpendicular is drawn from the right angle of the base, the triangles on each side will be similar. Okay, so what we see is that's kind of what picture B is doing. So put the second picture on its side. If you have a right triangle, like a big right triangle, and you draw something from the base straight up, that's what that is. So basically, right triangles are those two right triangles would be similar, right? So like triangle BDM is similar to triangle BAC. That's what proposition 2 is saying. Okay. Proposition 3 is in a right angle, the midpoint of the hypotenuse is equidistant from its 3 vertices. Again, second picture, because M is the midpoint of the hypotenuse, we get to see that M is actually equidistant from point C, point A, and point B. Does that make sense so far? Okay. So now we get to see what some of these propositions are starting to show. We see that that the triangle MAD and triangle MBD are congruent by a side angle side. So that's pretty important. Not necessarily the isosceles part, but we're going to focus on those two triangles being congruent, and that'll help us in a little bit. Okay, so now, again, we're going to have to shift because we're going to open it up quite a bit. So the next proposition doesn't even correlate to the propositions or the proof above. So this proposition is for strictly a quadrilateral, the one that you see, the third picture. So quadrilateral AHBO is a quadrilateral, and its diagonals, they make right angles from A to B and O to H with the legs. So again, we can say that the midpoint M is actually equidistant from those points. So M is equidistant from A, from O, from H, and B. So that is kind of important for the proof, and you'll see it actually come in the exact same shape. So that is super important. Okay, now proposition 5. The opposite angles of a cyclic quadrilateral, which we see is a symmetry. Okay, yeah, we covered that kind of. Okay, does that all make sense? Like we understand like the basis of these propositions. They're going to come in useful, I promise. Okay, again, the theorem is how do we prove this formula is true? Okay, cool. Okay, also I know that I'm missing parentheses. Sorry if that messes you up, but yeah. Okay, so part A, what are we trying to do in part A? We're going to see the link between a triangle's area and its semiperimeter. When I say semiperimeter, that's what I mean S to be. So like S equals 1/2 A plus B plus C. Okay, so yeah, so we already know that the angle of a triangle is 1/2 base times height, right? Like we already know that. And so from each triangle that we've made by the bisectors, we can take and find its area. So triangle AOB, like the bottom triangle, we can find its area from 1/2 the base, which is the radius. Sorry, the base, which is AB, and the radius, which is the height. Okay, so we can do that for each of the 3 triangles. So triangle COB, same thing. Triangle COA, same thing. Like we can find the area in terms of the base, which we're going to call C or A or B, and then we can add those together. Does that make sense? Like that's part A basically. Okay.
So the height is just the radius every time? Is that what you mean?
Yes.
So you're splitting it up into
3 triangles.
Into 3 triangles, each of which has a base equal to the side. of the triangle, and then the height is the radius of the circle.
Yes.
The dotted line.
Yeah, the dotted lines are like, but yeah, that's the triangle. So it's like the base of the original triangle, and then the dotted lines form the three triangles. Basically.
We're learning about Heron.
So this is a triangle right here. This is
Lost. Taking me out of the call. You sure that explains?
That
So
makes
I
sense.
class because
Oh, so I'm sorry.
the screen will go black and I won't hear anything, and they won't even notice.
Are you talking to me? Are you talking to us? Hello. Nice. Okay, cool. We're gonna keep moving. So fun. Okay. So that's part A. So part A again, semi-perimeter. How does that correspond to the area of a triangle? Part B. This is where we see that the semi-perimeter, the quantities of S minus A, S minus B, and S minus C are actually all on the triangle. So it's important to see that these are actually all particular segments. Yeah. So originally we can see that the bisectors help us create like congruent triangles, right? So these triangles right here are congruent. These triangles here are congruent, and these triangles here are congruent. Sorry. Yeah, that's like the best way I can explain it. Like those are congruent because originally they have like the same bisector of that angle, and then they share the middle side, and they also have right angle. So yeah. Okay. So the next thing that we can see is that we're gonna extend AB. And we're going to extend a G on it, okay? So AG is the same length as CE. This is really important because it can be confusing, but basically what this does is you'll see why it's important at the end, okay? But like we're going to extend it because that's going to be the side length of CE, okay? I'll explain it more. CE, this segment right here. We're going to take the same length, and we're going to put it right here.
Okay. Can I ask, like, can you use the stylus to write so people on Zoom can see it? You see how to do, like, if you touch the screen and touch the pen, you can actually draw on there and erase stuff.
Okay. Yeah, I can do that.
Okay.
This is fancy. This is above. Okay, this is a lot. Okay.
It's okay. Yeah. So can you try writing just to see if it works? You can always erase. Did you turn the pen on?
It's on now. Oh, it's already on. Okay.
Yeah.
Sweet.
There you go.
Beautiful.
You can erase stuff if you need to.
Okay. Yeah. So we're gonna prove that BG is the same as the semi-perimeter. That's why we extended it. It's because we're going to prove that BG, here it is equal to S. Okay? That's the goal of this part right now. And so so we say that the length of BD, so BD plus AD, which is this right here, plus AG. So this is what we just had. Is this equals BD plus AD plus AC. Okay, that's what we want to. That's what we're seeing. Okay, like I said, the segment from CE is the same as AG. So when we take 1/2 of 2BD, so 2 of these and 2 of ADs and 2 of CEs, that's where we get like that's like that's where we're seeing like it's the same equation basically, as they're all the same segments on that. So how do we prove that that's S? So when we keep moving, we see that BD and BC. So yeah, we gotta orient ourselves. So I'll do a few of these. Okay. Cool. Okay. Yeah, so 1/2 BD plus BE. So BD and BE, so these are the same. So this is the perimeter right here. So 1/2 the perimeter. So AD, again, AD right here, AF and then CF and CE. So this line right here is simply the perimeter. 1/2 the perimeter. Does that make sense? So that's where we're moving, okay? And then the only change that we have from this line is we're gonna say that these two are the same. Well, no, we're not gonna do that. We're basically just manipulating it. So like this comes here, this comes here, this comes here, and this comes here. That's all we do. We just commute property, changing around. And so when we look at BD and AD, we get AB. So AB, BC, and AC. That's a really complicated way of just like we basically all we're trying to see here is that BG is S, which is 1/2 A plus C plus B. Sorry, I know that can get really complicated, but that's what we're just trying to see, that the line BG is the same as those segments. Yeah.
You make it the same by measuring it, or is there a way that?
So what is AG? AG is just simply CE. So
You constructed that to be true.
yeah,
right?
yeah.
Like you just extended it out so that it.
It's by construction. So the semi-perimeter is just half of the perimeter. So when we look at the perimeter, it's just CB plus BA plus AC. We take half of that. Like that's the semi-perimeter. Cool? Okay. Nice. Okay. So again, this first picture is not the one that you're going to reference yourself to. I just want to show that, like that first picture, this one right here. Markers. This first picture right here is just showing that these are actual segments on the triangle. Originally, when I see that first one, I'm like, where are these segments at? But this first one shows us like what these segments kind of will like look like basically. So again, down to the nitty gritty. A minus C. So we defined C already to be AB. Right, like this is side C right here. That's side C. So side C minus S minus side C is just simply AG. So that right there. Right, like that's all we have left from BG. That makes sense?
Because BG is S.
BG is S, yes. So it's just simple substitution, but these are actual line segments. Okay. Okay, and we'll do that for so we did S minus E, S minus B is the same thing. So the BG, which is the semi-perimeter, minus AC, which is right here, you're just gonna get BD. Okay, same thing for S minus A is the semi-perimeter minus BC. You're just gonna get AD. Like you're just gonna get those segments. So these are real segments. That's the important part of part B, is that ultimately like we have real segments for S, for S minus C, for S minus B, and for S minus A. And that's where we get them from. Like they're not just like, poof, here we go, but like they're segments AD and AG. So these segments will actually show up in part C. So that's why we need to know like S minus C is AG, S minus B is BD, and S minus A is AD. So keep that in the back of your mind. That's where we're gonna go, okay? Cool. Cool beans. Okay, part C is where we get a little, there's a lot of fun that comes into this one. So
Brett, can you move Hannah's picture? Like, you can.
yeah, I gotcha.
You can just go up.
Does that work?
Yeah.
Nice. Okay, here we go. Part C, the last part. Okay, so now we're gonna extend this triangle by drawing the perpendicular from LO. So we're gonna draw basically a perpendicular from this line. This line's perpendicular is simply right here. Okay. Oh, that was close enough. Okay. So yeah. So yeah. So this is OL right here. That line that I just drew, that's OL. Okay. And now we're gonna draw another line that is perpendicular to this, which is AB. And so this perpendicular is right here. Okay. And now we also see that we're gonna connect B right there. So sorry, not great, but okay, this is the quadrilateral that we saw originally, right? Like you see how like this is like these are why the lines have been drawn, is because we want to see this quadrilateral again, because we know stuff about it basically. So this is also really important that we see point K right there. And so that point K is equidistant from A to R. Yeah. So well, I don't know if that's right. No. Sorry, scratch that. We're just gonna keep going. Stick to the notes. Sorry. Yeah. So basically, we get this quadrilateral such that these two right angles right here and right here exist. So we can also say that, okay, think about a triangle. What does the triangle's angles add up to, right? 180. What does the circle's angles add up to? They add up to 360. So that's kind of like the basis of this part right here. Okay. And now we can say that, yeah, we go crazy with the Greek letters here. If I erase if I take away the quadrilateral, you guys still see it? Okay. So yeah, we go kind of, it's kind of hard to track with the Greek letters. I ran into that the first time. So basically this beta right here, right there, plus the lambda right there, that's going to give us, yeah, that's going to give us AOB. Okay, so let's give us that angle right here, and then we can say that we can also say that angle A plus this is going to be two right angles. Okay, so sorry, angle alpha, that angle right there, that angle will end up giving us two right angles. We can see that because like we have half of the circle. So yeah, so like the lambda plus the beta plus the alpha is going to be 180 degrees because it's half of the circle. So that's because like, so we can say that will equal two right angles. Okay. So this is very crucial that we can see that angle angle alpha is the same angle as angle AHB. So where's angle AHB? Angle AHB. You see how this right here is the same as this angle right here? Like they're the same angle. So this seems insignificant, but it's very crucial. Does it make sense how I got there, or how Heron would have seen those two as congruent? Kind of.
Why are they congruent?
So we get to see that. Where's it at? So when we take this this right here, it gives us like basically 180 minus alpha, right? Oh, Sorry. My bad. Okay. So, yeah, so basically when you get this, that equals angles the beta plus the Greek, the lambda. So does that make he's just saying that these two are congruent. I'm trying to remember what the how he said it was congruent. I'm blanking. I'm sorry. Yeah, I'm not 100% sure, but like basically it's more of like it's not like that these two right angles, or sorry, that this right here is 180, and that we can find that this is also going to be that same angle. I don't know if that helps.
Sure, it probably has something to do with the angles in a quadrilateral, like some property that they have. So
Yeah.
One of those propositions that you have.
Yeah. Okay. So then this gives us that because this angle is the same right here, then we can say that triangle COF is similar to triangle KOD. So this triangle right here. So those two are similar. So there's a right angle right here. Yeah. So these are similar. So that this we know that this is when the proportions come in, and so it'll get a little bit confusing and it gets a little tough. So we know that AB, so this whole line segment right here, is proportional to AH. So AH, which is right here. So this doesn't show up. Okay, we're clearing it again. So this is proportional to this, which is equal to the proportion of CF and OF. OF, yeah. Sorry, that wasn't the right line. CFOF. Okay, so we see that these are proportional, the same as AG and R being proportional. This is equivalent to saying that, so you see where we got, this is the important part right here, is that AB and AG are proportional to AH and R being proportional. So R being right here, okay? So that these are equivalent. We note that we have another set of similar triangles here, and then it's just the same process of we're gonna say that these two are proportional because we know that these are similar, and R over KD. So this is what we get from the result here. So when we compare this set of ratios right here to this set of ratios right here, we combine them and we get this step right here. Okay, so ultimately, this first set of part C comes in sets right here of the segment AB is AB over AG. So again, AG is equal to AK and KD. Okay. So that's where that's kind of like, again, we're gonna blow it up. I know it's a lot right now, but that's kind of the proportions that we want to that we've seen. They come together and they end up being equivalent. Okay. Okay. Now this is the last part where everything kind of starts to come together. So then we know that these two triangles right here, which are similar, give us the segment KD times KB, which is just R squared. So where's triangle KDO. KDO is right here, okay? And triangle ODB is right here. Yeah, right here, okay. So we get to see that these two are also similar. So KD, this segment right here, times BD, which is right here, just give us R squared. It's just two R's in there. And so we can also add one to both sides. So this is the equation we had on the last slide, and we just get to add one, which is just we're going to use the form AG, and on this side we're going to use the form KD. So it's just adding a form of one to both sides. Okay, so that stuff's really important because it gives us this situation right here. Okay, so BG, so this what we've called S basically, and is proportional to AG. So this right here, cool, is the same as saying AD is proportional to KD. So KD is where's that at? KD is just right here, this little short one right there. Okay, so if you're following, then we can give us the equation from right here. We combine it with this right here. We get this equation right here. Okay, so that's kind of the culmination right here. We're gonna start putting everything together. Okay, so what we see this equation is we can just cross multiply it. Okay, so BG squared times R squared is just right here. These two multiplied to each other are just this right here. So R squared is just the radius squared. BG squared is just S squared, because we said that earlier. And now we're going to see that we can just reorganize it. But we also get to see that, okay, what is AG? We said that was SC in part B. We said that BG right now was just S originally, right? We can say that AD is S minus A, and we can say that BD was S minus B from the last part. Okay, so I know that was a lot how we got there, but we end up getting K equals the square root of S minus A, S minus B, S minus C. So yeah, that's
So R is a radius.
yes.
S is a semiperimeter. That what you had before was like you had like a side length times the radius times a half, right?
Yeah.
For each one of those like dotted line triangles or something like that, right?
Yeah.
And so when you add all those things together, you get the area of the whole triangle, right? And the height every time was the radius.
Right.
And when you just take half side length times the radius, half side length times the radius, half side length times the radius, and you add those together, you get the entire area. But if you take half and you take side length plus side length plus side length, that's just the semiperimeter, right? So that's where that RS formula comes from.
Right.
Okay.
Okay, and that is so now Hannah will do her part.
Okay, awesome. That was crazy stuff, Brett. So big thanks to you for figuring that all out. You did a great job presenting it to everybody. So as we saw, it's a very complicated proof there, but super interesting fact is that it can actually be connected to the Pythagorean theorem, which is really surprising because like that's talking like strictly about right triangles, and this proof that we just went through is talking about like the area of all triangles. So really cool. I'll walk you through it pretty quickly because we don't have a whole lot of time left. But so essentially, like you see there on the right side of the screen, just a basic triangle, and we know that the semi-perimeter is a plus b plus c all over 2. And if we just like rewrite some stuff, so if we wanted to find like what s minus a is, it'd just be a matter of like subtracting a from that the right side of that equation, and then if you like put that over 2, it'd be like minus 2a over 2. So that gives us negative a plus b plus c. And then the same thing can be done there with for s minus b and s minus c. And those are like the crucial parts of Heron's formula there. So then if we multiply that all out, so if we did like s times s minus a times s minus b times s minus c, using these new like formulas that we got, we can find that big nasty fraction there in the middle of the screen with like the 2a squared b squared plus 2a squared c squared and so on. And that's all going to be like under the radical sign from Heron's formula. And then if we just like square both sides, we know that k squared, which is the area squared, is going to be equal to that big fraction. And also we know from like previous proofs that the area is 1/2 base times height. In this situation, b is the base, c is the height. So bc over 2 is going to be area. So if we square that, because it's equivalent to k, so k squared, that formula squared is going to be b squared c squared over 4. So now we just have to set that big fraction in the middle equal to b squared c squared over 4. And that gives us there the second to last line, starting with like 4 b squared c squared is equal to blah, 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 blah. And that was just done by doing like some cross multiplication and then a little bit of reducing. And I just put some dots in the middle there, so I don't have to write everything out. But essentially, it's just a matter of bringing everything to one side, so it's all equal to 0, and then doing a bunch of just reducing and that kind of stuff, and you end up with b squared plus c squared quantity minus a squared is equal to 0. It's crazy how that all works out, but it does, I promise you. And then you just bring a over to one side, and that gives us a squared is equal to b squared plus c squared, which is exactly what the Pythagorean theorem says. So yeah, I was saying it's super interesting that that those two coincide, because they seem kind of unrelated at first, because one's about area and one is about just like finding the length of a hypotenuse, or like the length of a side of a right triangle. But they actually work very well together, which is really cool. All right, you can go to the next slide. Awesome. So this is going to be just a last bit of additional info. So there's a lot of big words and another language on this slide that I'm not going to try and pronounce. But essentially there's this Islamic scholar who credited this formula, Heron's formula, actually to Archimedes, which, I mean, who knows, maybe it was him, maybe it wasn't, but we're all just kind of at the point of Archimedes has enough credit going for him, so like, why not give Heron the spotlight for a little bit? No matter who proved it, it's an amazing proof that is so useful now. So yeah, that's just kind of funny that yet again people are trying to give the attention to Archimedes. And so moving on throughout history, as the end of the Roman Empire happened, that kind of brought about the end of the Alexandrian library too, which was like very crucial part like of mathematics at that time. So it was first like closed by Christians in 529 AD, just because they had a lot of like pagan documents in it, and that was kind of like the reasoning for shutting it down. And then in 641 AD, it was burned down by the Arabs. And there were many items saved, but also a massive amount of items and documents that were lost to the fire. And so many scholars now are like, why get rid of all of these amazing proofs and amazing documents that we could be using today? But that's going to be the case for so many different just situations in history whenever things are destroyed. So I said like it was the Arabs who burned that down. It's kind of interesting because they were kind of the next center of mathematics once the Roman Empire ended. And so they started like translating a lot of the classics. So there was like the Elements, which we went over by Euclid a couple weeks ago. And then there's Syntaxis Mathematica, which was written by Ptolemy, but it's kind of like, it's a mimic of the elements, but about astronomy instead, which is really cool stuff. And then another fun fact is the House of Wisdom was kind of like the Alexandrian library, but like for the Islamic Empire, but it was in Baghdad. So it's kind of just like a place where all of the scholars met together and like talked about really cool like philosophical or mathematical concepts and stuff. So yeah, it was like a replacement of like Plato's Academy or the Alexandrian library. So now we get to look real quickly at the like most important Arabian mathematician, who is that name there, Muhammad ibn Musa yep. But he actually is kind of like the father of algebra. As we've seen so far, the Greeks and the Romans didn't do a whole lot with algebra, more so the Romans and the Greeks, obviously. But it's really cool because he actually was he like illustrated the solution for both linear and quadratic equations. And he gave us the quadratic formula, which, you know, can be used to solve for x in like a quadratic equation. So super, super awesome because we use that so much now. And so another cool thing is that he presented all of this verbally. He didn't like write it all out. He just talked through it all with like crowds around. And yeah, so we can see like the name of his like presentation there is like the first bullet point under his name. So that's it in his language, and then translated into Latin is the Ludus Algebrae et Algebraica. Okay. And yeah, so we just kind of reduced that to algebra, which is what we call it today, obviously. So super awesome that I never realized personally that algebra came from the Arabs in the Islamic Empire. But yeah, so it's kind of interesting because the Arabs did a lot for mathematics, and they can kind of be compared to the Greeks in a different way, but ultimately we think that like the Greeks kind of contributed more because they just made a lot more like quantum leaps throughout mathematics. They focused on lots and lots of proofs, while the Arabs didn't necessarily do that. But it's very cool because the Arabs sort of reduced like Roman mathematics to just like Roman numerals and clock faces and stuff, and like the Arabs really made math what it is today. So yeah, and then after the Arabs kind of like started on their decline, Italy was like the new center of mathematics. This kind of happened like after the Christian Crusades, and many documents like throughout these crusades were found, both like classic documents and like more of like the modern documents that like the Arabian people made, and so through the crusades a lot of those documents were found, and that kind of all culminated together to create like mathematics what it is today. So yeah, that's basically going to lead us up into next week, and what we'll be learning next week through this book. But yeah, have any questions about anything?
Thank you guys. Appreciate it. Thank you, Anna.
Yeah, thank you for figuring this all out with me.
All right, thank you guys.